Okay, so where are we? Good. Okay, so yesterday we finished by stating the Kraft-McMillan inequality. So this is, I've tried to add some dates to the course this year. So Kraft proved a version of this in 1949. McMillan looked at this in 1956. So you can see this is well under 100 years old. And basically everything we're seeing in this course, or most of it, it really developed along with computers. That's why people really cared about this. It's the development after the Second World War of radio communication and computers, which led to all of this work. Okay, so the Kraft-McMillan inequality says, if I give you any uniquely decodable code, C, and I set Lx to be the length of the code word for each x, then it must be true that when I take I sum over all code words, and I take the size of y, the alphabet that I'm using as my output symbols, size of y to the power of minus Lx, add that up over all x's, I must get something less than or equal to 1. So this is true for every uniquely decodable code. Conversely, given numbers which satisfy this, so if I give you a finite set y, an alphabet, and that defines this, and I give you some set of numbers such that this inequality holds, then there is a prefix code which has exactly those code word lengths. So we've got if and only if in this sense. Okay, so let's see the proof. Okay, I'm going to set d to be the size of y so that I don't have to write so many things. And I'm going to write L max is the maximum over x in x of Lx. Just saves us writing quite so much. So consider some source message of length n. So let's consider a source message of length n. Okay, then what am I going to get? Well, then if I calculate, so the sum over x in x, so I'm considering all of my source messages of length n, d to the minus Lx to the n. So if I compute this, what is it? Well, I can expand this. So this is the sum over x1, x2, all the way up to xn of d to the minus L x1, d to the minus L x2, all the way up to d to the minus L xn. This is just expanding out this power in terms of putting different indices and summing over all of them. So nothing going on here. Well, of course, I can write this as the sum x1 through to xn of d to the negative sum of Lxi for I equals 1 to n. Okay, so I'm considering a source message of length n. Okay, so I'm summing over all possible ways that source message could occur. I consider this, I write out all the different terms, and I get a sum, which is just this sum here. Okay, so I've considered all the source messages of length n. Let's restrict to those that have outputs of length k. So the output string, if I give you an input of length n, this is going to be the corresponding output length. So just adding together the lengths of each of those terms. So this thing here is output length for source x1, x2, up to xn. Okay, and I'm summing over all possible source terms, and I'm just getting each of these to be there. So restrict attention to those source strings of length n with output length k, which is then just, as I said, the sum I equals 1 to n Lxi. So this is the source strings such that this is the exact length we get. And we write a k for the number of source strings of any length with output length k. Okay, so if I think about the source strings of length n, then I'm going to get something that looks like this with a sum up to n, but then I'm going to write ak for how many inputs are there which have output length k. The reason for doing this is going to be because of the following. So now I'm going to write the same thing that I wrote a moment ago. So the sum x in x d to the minus lx to the n. Well, this has to be less than or equal to the sum from k equals 1 to nl max. So if I think about all of the strings of length n, what output lengths could they be? Well, they could be length 1 up to length n times L max. That's the longest string I could get as an output. Well, so how many, this is adding up the total lengths, or d to the power of the total lengths of the output. So I'm going to get ak, there's ak strings which give me length k of any length, so that's certainly bigger than the inputs of length n that give me length k. And then I'm going to have, for each of those terms, I'm going to get d to the minus k. So here I'm adding up now. So here I'm looking at all of the source strings of length n, and I'm computing this quantity here, okay, which is just d to the minus k. But now if I add this up and I say, well, this was for sources of length n, I can bound that by looking at sources of any length which give me exactly length k outputs, and I get a bound that looks like this. Okay, that doesn't seem like I've done much, but I know that my code is uniquely decodable. So as my code is uniquely decodable, what do I know about AK? Well, I know that, so I can count how many strings there are of length k. And there are d to the k strings of length k. So you can't have more inputs than you have outputs, or you're going to have a conflict. So if I have more inputs than I have outputs, two must go into the same place, and I lose unique decodability. So by unique decodability, we know that AK must be less than or equal to d to the k, which is a very crude bound, but it's a bound that is therefore true. Okay, hence, I can take this bound, plug it in here, get an extra bound. What's this going to do? I'm going to get that the sum of x in x, d to the minus lx to the n. So this was counting over all the strings, all the output lengths. This must be less than or equal to, well, if I substitute in d to the k here, these cancel out. This sum then turns into just n times L max. But I can take the n through to both sides. Taking the n through to both sides, this implies that the sum x in x d to the minus lx is less than or equal to n L max to the 1 over n. Notice that there's no n's on the left-hand side. All the n's are on the right-hand side. This has to hold for every value of n. So I send n to infinity. And I get 1. Done. And so this is the proof of statement 1. So what we've done is we've just used unique decodability. Unique decodability tells me how many things there could be having length k. I use that to rearrange, and I get out by the pigeonhole principle a bound of this form. Okay, so that's the first half. The second half is somehow a little bit more interesting, because what we're going to have to do is construct a prefix code. So we're going to do this by explicit construction. Okay, so now we're going to show 2. So let Lx be integers satisfying star. Okay, I'm going to make my life a little bit easier by relabeling everything. So by relabeling, set x to be equal to the, well, there's, how many terms are there? Well, there's mod x. I can just make them 1, 2, up to the size of x. I'm just going to say this is the set. If it was something else, I'm just labeling them by these numbers. But I'm going to do a little bit more. I'm going to sort the probabilities, the code word lengths, and assume that L1 is less than or equal to L2 is less than or equal to ... is less than or equal to L of the size of x. So I'm just going to sort these numbers by the lengths of their code words. I'm allowed to do that. It's just a sorting, a rearrangement, a relabeling of my inputs. Okay. Define Rm to be the sum from I equals 1 to m minus 1 of d to the power of minus Li. This is a quantity we're going to see a few times. What do we know about this quantity R? Well, by assumption, it is less than or equal to 1 for every m. So it's increasing, it's less than or equal to 1 for every value of m. And in fact, if I drew a picture of it, I would get, so here's the interval from 0 to 1. And here is R0, or R1, sorry. Okay, there's nothing less than it, so it starts at 0. And then I get R1, R2, R3, up to R mod x. Okay, and then there might be a bit left over on the end. But here are the numbers that I'm working with, and you'll notice that the distances between them are decreasing because of the way I've ordered my code words. So what am I going to do? How am I going to define a code? Define Cm as the first Lm digits in the base D expansion of Rm. Okay, so I need to be a little careful when I talk about base D expansions. I'm assuming that I don't get infinitely many copies of D minus 1. So if D is 2, that means I don't get an infinite string of 1s in my sequence. Okay, I will always have infinitely many zeros. If D is 3, that means I don't get an infinite sequence of 2s. Okay, just because I need to make sure I have a uniquely defined object. And then I take this to be the first Lm digits in that expansion. Okay, so that is, let's be careful, Cm is y1, up to ym, where Rm is equal to the sum I equals I greater than or equal to 1 of yi d to the minus I. So I've just replaced this by the binary expansion that I'm getting out of here. So my claim is that this is a prefix code. Okay, why is that? Well, we're going to use the fact that I have identified my points in this way. So if I tell you that my number, okay, we'll do this two ways. We'll do this the way in the notes, and we'll also do it a sort of more geometric way. If I tell you the first LM digits of a point, that identifies an interval in this row, in this space. Okay, so if I tell you if d equals 2 and c of m equals 1, 0, what does that tell me? Well, I'm at, so 1, 0 corresponds to 0.5. And I've got 2 digits, so I know that I've got I'm at 0.5, which is here. And the claim is that if I go out in that interval, which is from 0.10 to the next digit, which is 0.11, there's only going to be one code word in there. And that's the graphical version of what we're doing here. Okay, so I know that the code word starts with 10, or the R of the code word starts with 10. There's only one code word that does that, so I know I've got that code word. And that's the picture. Okay? That means it has to be prefix, because there's no other code beginning with 10. Okay, so formally, if there exists m less than n, and cm is a prefix of Cn, then the first Lm digits of Rm and Rn agree. Okay, they must agree because this is how I've defined the code words. That means, hence, Rn minus Rm is less than d to the minus Lm. Notice I can use the smaller version here. I can use the smaller number because I've ordered my code words. So Rn minus Rm must be sufficiently small so that they agree in the first Lm digits. Okay. But we know that Rn minus Rm, which is the sum I equals 1 to n minus 1 of d to the minus Li, that is at least d to the minus Lm because everything's ordered. Is that right? Sorry, it's from m there. Okay, so from m up, this term I must get this. Here's a crude bound. I look at those two and I have a contradiction. Done. So we've now proved the Kraft-McMillan inequality, and conveniently we've also constructed a code. We will come back and see this code again later. So corollaries to this. Any uniquely decodable code, there exists a prefix code with the same code word lengths. Easy statement that we've just proven. This is called as I say, the Kraft-McMillan inequality. So Kraft's original version in 49 doesn't deal with uniquely decodable. He just dealt with prefix codes everywhere, which means that you've got a slightly easier proof than what we gave. You don't need to use this pigeonhole principle. But McMillan showed that it generally holds for uniquely decodable codes as well. Any questions about that? Because we're going to now move on to the next topic, what we need. Everyone happy? Good. Okay, so the next thing that we need before we start actually constructing codes is something called the asymptotic equipartition property. Okay. So the idea here is if I just tell you I have a sample from a distribution, you can't tell me much about the distribution. I tell you I've rolled a die which might be fair, it might be not. You probably can't tell me very much about it. Okay, you observe a 3. All right, that's all. Whereas if I take the same die and I roll it 1,000 times and you observe the distribution, you can probably tell me a lot. So you can identify the distribution a lot more closely. In fact, you can say that the frequency with which you observe 3s corresponds to the probability that the die will roll a 3. So that's the law of large numbers. And what we're going to do is we're going to try and use the law of large numbers for encoding sequences. What does that mean? It means that we're thinking the fact that we've got a sequence tells us information about the problem which we wouldn't have otherwise. We know there are certain outcomes which are extremely unlikely to occur, and so we can restrict our attention to those that are likely to occur, or more likely to occur. Let's see a quick example. So sketch example. So X is a Bernoulli 0, 1 valued random variable. Okay, so we've got coin flips, they're 0 or 1 with some probability. X1 through to xn iid copies of X. So I've got a sequence of coin throws here. So a sequence of observations, I take x1 up to xn, occurs with probability. So the probability that x1 through to xn are exactly equal to little x1 through to little xn. What is it? Well, it's equal to p to the power of the sum indicator xi equals 0 times 1 minus p to the power of the sum xi indicator xi is equal to 1. So I just count the number of zeros, I count the number of ones, p to the power of the number of zeros, 1 minus p to the power of the number of ones. There we are. Okay. But by the law of large numbers, if n is large, we know that the sum xi equals 0, so 1 over n times the sum from I equals 1 to n, that's going to be approximately equal to p. If I count how many zeros I've observed and average it out, I'm going to get approximately p. That's just the law of large numbers. And similarly, 1 over n sum indicator xi equals 1 is approximately 1 minus p. Okay, so if I've got that, hence the probability x1 to xn to xn, this probability is going to be approximately, at least, p to the power of np times 1 minus p to the power of n 1 minus p for most cases. So I'm being very sloppy here because I've used the law of large numbers to say I think this is going to be true, and it's sort of true for most of the reasonably likely things that would happen here. It's very unlikely that I observe a sequence which isn't where it's going to look like this. So for most of the little x's, most of the observations that I care about, this statement of probability is going to be true. And you notice that this is a constant. Okay, so for most of the things that I care about, the observations that I could care about, I'm going to get a constant probability.
Have we ordered the x's?
Nope. Oh, so the x's come ordered. It's a sequence of coin toss. This is the first, the second, the third, etc.
I mean, the right-hand side is ordered as well.
The right-hand side, this is just a number.
The x1s, xn.
Here, these are ordered, yes, but you can see because it's summed, it doesn't matter if it's ordered or not.
I mean, because if this statement is in conflict with the previous one.
I am waving my hands at this point. I am not making a rigorous statement at all. I'm sort of saying, oh, look at the moving parts and let's hope that they work out. And I'm sort of sketching out that for most of the x's, whatever that means, I'd expect this sort of thing to happen if I didn't care about proving anything. We're going to prove it in a minute. Okay, and then we'll be more rigorous. So if I take a logarithm, what do I get? Well, I get that minus log of the probability minus this, that is approximately equal to np, or minus np log p minus n1 minus p log 1 minus p, which is n times hp, where h is the version of the entropy we defined where I can put just a number in and it evaluates to this thing without the n's. So if I divide everything through by n, this should be, for most interesting sequences, provided n is big, this will be close to the entropy. Okay, and that's just the law of large numbers. So for a typical x1 through to xn, well, I haven't said what typical means. We should have that the probability x1 through to xn equals x1 through to xn should be something like 2 to the power of minus h n h of x. Okay, the entropy of my individual object x, which is the same as hp. What we're going to do is we're going to try and make sense of this and make it a little bit more rigorous in what comes next. So, a couple of things before we do that. First of all, how many of these sequences are there? Well, you look and you see this probability, they're sort of all equally likely, and this is a whole lot less than 2 to the power of n, because h is generally going to be less than 1. So this probability is a whole lot higher than 2 to the minus n, which means that unless p is equal to a half, in which case it is 2 to the minus n, I've got a whole lot more probability than I thought I would have to begin with. So I'm getting all the probabilities somehow accumulating on certain typical sequences, and there's not so many of them, which is one thing that we're going to get. We also have this idea, typicality. We haven't defined it, so we can somehow restrict our attention to these typical sequences and not worry too much about the rest. Okay, let's try and do this a bit more properly. So, first theorem. This is the weak AEP version 1. Okay, let x be a discrete random variable, then minus 1 over n log probability xn, so I should say for x1 iid copies of x, the probability of observing the particular sequence through to xn. So this is the probability that I observed the particular sequence that I did observe. This probability converges to h of x in probability as n goes to infinity. Everyone happy with convergence in probability? You should have seen it last year. Okay, so proof by independence. So minus log, let's write out this probability, x1 through to xn. And this is equal to minus the sum, I equals 1 to n, log px of xi. They're all IID, so they're independent, so I can just add the probabilities together, or multiply the probabilities, hence add the logarithms of the probabilities together. And they're identically distributed, so this is just the probability. It's the same function for all of them. But now I look at this and I go, hang on, these are themselves random variables. They're reasonably well-behaved random variables. It's just some function applied to xi. I am now taking a sum of them. We know that the sum, and we can say the expected value of minus log px of x, well, that was one of the representations we had for hx. Okay, so it's fairly clear what we're going to do. You divide both sides by n, then I apply the weak law of large numbers to say this converges to this. Okay, so result follows from the weak LLN. I could do a strong version, so if I know the strong law of large numbers, I could show that this converges almost surely to this right-hand side, but we're not going to worry about that too much. Strong law of large numbers is not so exciting for us today. Okay, so that tells us that with high probability, this quantity is going to be close to this number. So we're going to use that to define what I mean by a typical set. A typical set is when this quantity is close to this number, where what do I mean by close? Well, I'm going to have an epsilon, and I know that's going to happen with high probability, which means probability 1 minus epsilon. Okay, so we get to a definition. Okay, for any n, natural number, we call, so I'm going to define what I mean by a typical sequence, T epsilon n. So these are going to be the typical sequences of length n with a tolerance level epsilon. This is the set of x1 through to xn. So it's a sequence of length n, such that I know I'm converging. I'm going to want to have minus 1 over n log p x1 to xn evaluated on this sequence. Should be close to the entropy of x. There we are. We can say less than or equal to. Doesn't really matter. So I'm going to say I've got a typical sequence if it's a sequence where this quantity is close to the entropy. Okay, so that allows me now to, so we call these typical sequences of length n with error epsilon. So now I can state the more interesting version of the AEP. So this is Shannon, 1948. Okay, so for all epsilon greater than 0, there exists an n naught in n, such that for all n greater than or equal to n naught, three things are true. The first is, well, this statement holds. So the probability x1 through to xn of x1 to xn is in the interval 2 to the minus n times h of x plus epsilon up to 2 to the minus n h of x minus epsilon. So the probability has to be pretty close to 2 to the minus n times the entropy. So 2 to the minus n of the entropy. 2. So this is for all x1 through to xn in the typical set. So for any typical sequence, this holds. 2, the probability that you observe a typical sequence is greater than or equal to 1 minus epsilon. And 3, the number of typical sequences is between 1 minus epsilon times 2 to the n hx minus epsilon and 2 to the n hx plus epsilon. Moreover, for point 1, we can take n naught equals 0. We don't need to take the limit for point 1. So this is the asymptotic equipartition property, the proper one. So we've got three statements to prove: the probability, the bound on the probability that we have a typical sequence, and we have to count the number of typical sequences. Okay, let's get on with it. So point 1 directly follows, so this is the proof, from the definition of T epsilon n. Okay, since the probability that x1 through to xn is not a typical sequence is equal to the probability that, no, that's from the definition. Point 2 follows from the weak AEP. Okay, since the probability you don't have a typical sequence is the probability that the absolute value of log p x1 to xn of x1 through to xn minus h of x is greater than epsilon. So point 1 and point 2 are really just the definitions. No work needed. So the only really interesting one, so here this is just rearranging the definition of this. Here this is, well, is the probability there? Yes, you just take it from, we know the weak asymptotic equipartition property says I have convergence, so I pick everything big enough to make sure I'm close enough, and there we are. What about point 3, counting the number of typical sequences? Okay, so for point 3, what do I need to do? Well, let's let's calculate some probabilities. So 1 is the probability, if I think about a sequence x1 through to xn, if I sum over all possible sequences I could observe, I must have probability 1. So this is the probability. I'm just not going to write this subscript because I'm lazy. x1 through to xn. I know that this is probability 1. I have to observe something. Okay, well, let's restrict our attention. This is certainly bigger than if I just sum over the typical sequences. So if I just sum over the typical sequences, I must get a smaller number. But now, I know that these probabilities, hang on, we've just shown something about those probabilities, we've got a bound on them. So this must be greater than or equal to the sum over x1 to xn in t epsilon n of 2 to the power of minus n hx plus epsilon. Just using the crude bound that we've got in point 1 here. So I've used the lower bound. There we are. And this, hang on, those are constants. They don't depend on which particular sequence I'm looking at. So how many of these are there? Well, there's precisely t epsilon n of them times 2 to the minus n h of x plus epsilon. So now you rearrange this and you get the upper bound on t n epsilon. Because I just divide through by this. There we are. So that gives me my upper bound. I know that there's at most this many typical sequences. On the other hand, I can prove there's at least that many. Okay. For the lower bound, we know that the probability to xn goes to 1. Okay. I know that this probability goes to 1 as n goes to infinity because we have our bound here. So I can take my bound, so I get this. Okay, or at least 1 minus epsilon, but I can tie epsilon to n. Okay, so, or better yet, let's not do this. Let's go, it goes to something above 1 minus epsilon. I don't know how to write that. Something bigger than this. Bigger than that. Okay, so for n large, we know that 1 minus epsilon has to be less than or equal to this probability. x1 through to xn, this probability is in t epsilon n. So this goes above here, so this must be below this, which, well, okay, this is less than or equal to, let's use the bound on our probabilities again, the sum x1 dot 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 to xn in t epsilon n. So sum over all of these. Well, I have a bound on the probabilities. It's 2 to the minus n h of x minus epsilon, which is equal to 2 to the minus n h of x minus epsilon times t epsilon n. And we're done. We've got our bounds on the number of typical sequences. So there's a variety of ways we can interpret this. Well, what does this tell us? When n is very large, when we're thinking about a long sequence, it tells us that that sequence is almost drawn uniformly from a smaller set. So I have a set of these typical sequences. There's not so many of them. How many are there? Well, 2 to the n times the entropy. That's generally going to be a lot smaller than the number of sequences. Okay? Entropy is small. Okay? Unless my sequence is uniformly distributed, this is going to be a lot smaller than the number of inputs of length n. So if my original sequence is not uniform, this is going to be a lot smaller than the number of input sequences, and the probability of each of them is pretty close to just being uniform. So all the probability is either you've got these big mass of typical sequences, all pretty well equally likely, and then you've got all the other sequences which are very unlikely to happen. And the number of typical sequences is quite a lot smaller than the total number of sequences. And that's great when it comes to coding. We know where we need to focus our attention. We can code the typical sequences efficiently. We can not worry about the atypical sequences because they're pretty rare. And when it comes to coding the typical sequences, we don't need to worry too much about doing that because they're all equally likely. We just make them all equally likely and we're good. So that was Shannon's idea. Now, there's a few things, though, that we should be careful of. This does not mean that most sequences are typical, because we've thrown away a lot of sequences. In fact, most of the sequences get thrown away. They're just very, very unlikely. It's also not true that the most likely sequence is necessarily typical. If you think about tossing a coin, if I've got a biased coin, so heads 60% of the time, tails 40% of the time. If I toss that coin 10 times, the most likely thing to happen, if you think about it, is heads, 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 heads. So it's a sequence of heads. So, and that's if I throw it 10 times, if I throw it 100 times, if I throw it 1,000 times. The most likely sequence is a sequence of heads. But that doesn't converge to 60% of the time I get heads and 40% of the time I get tails. So the most likely outcome doesn't satisfy the weak law of large numbers. It just becomes very, very unlikely. So we're doing something a little bit sneaky by restricting to this typical set, which is where all my sequences are converging correctly. All right. So we're almost out of time, but I'll just make a couple of comments, which we'll finish at the beginning of next week, about strong typicality. Because of what I just said, maybe you say, I don't want to talk about typical sequences the way we've just defined them. We'd like to talk about the most likely sequences. Okay, so we can say denote definition by S n epsilon. I'm going to pick out the most likely set of sequences. So this is the smallest subset of xn, smallest in the sense of containing the smallest number of sequences, the fewest sequences. The smallest subset of xn such that the probability that I'm in S epsilon n is greater than or equal to 1 minus epsilon. So I'll throw away the least likely sequences until I just get down to the smallest set where I've got at least this probability. Throw away as much as I can. Okay, then we get a proposition. Let En be a strictly positive sequence with the limit of En as n goes to infinity being 0. Then, well, how big is this set Sn? Well, what we can say is that the limit as n goes to infinity of the limit as m goes to infinity of 1 over m times the log of the size of S epsilon n, length m, over the typical sequence, epsilon n m, is equal to 0. So what does this mean? It means that if I think about how big the set S is, the smallest set containing at least 1 minus epsilon probability, and the typical set, the multiplicative difference, so if I take the ratio, take the log, so this is the difference in the log sizes. When I average this out by the length of the sequences that I'm thinking about, then as m goes off to infinity, these two things might be different, but as epsilon goes to 0, they end up being the same. I don't asymptotically have any real difference. There's no real benefit of looking at the smallest set versus the typical set. And the advantage is that the typical set is often a little bit easier to work with. It's easier to get my hands on those elements because they're defined by this. I've got an explicit description of every element that's in my set, and I know something nice about it. Whereas if I talk about the smallest set, I don't know properties like this. I don't get a equipartition. I don't have constant probability of those things. I don't end up with a nice object to work with. So generally, we're not going to work with Sn very much at all. We're just going to work with the typical set. The proof of this proposition is in the lecture notes. I'm not going to go through it in lectures. You can read it. It's just a sketch. It's more for your information and seeing how these things work together, which means that next week we will start building codes. So we'll start explicitly building some codes for some things and seeing what they do and how we can build good codes, optimal codes. See you then.